Picture this: a vast cosmic web, stretching billions of light years across, where galaxies huddle together like islands in an endless sea. Among these gatherings, one stands out not for its brilliance, but for its secrets: the Coma Cluster. Nestled in the constellation Coma Berenices, this colossal assembly of galaxies is more than just a spectacle for astronomers. It's a treasure chest of enigmas, defying our understanding of the universe at every turn. What if I told you that within this cluster there are forces at work so strange, so inexplicable, that even the sharpest scientific minds are left scratching their heads? The Coma Cluster isn't just another dot in the sky. It's a cosmic puzzle, one that challenges everything we think we know about gravity, dark matter, and the very fabric of space itself. Here, galaxies move in ways they shouldn't. Here, invisible matter tugs at the visible universe like a puppeteer pulling unseen strings. Here, entire galaxies vanish into ghostly halos, leaving behind questions with no answers. This is a place where the rules of physics seem to rewrite themselves, where mysteries pile up faster than we can solve them. And today, we're diving headfirst into the heart of these riddles, uncovering 25 of the most baffling phenomena lurking within this cluster. But why does this matter to you? Because the Coma Cluster isn't just a faraway curiosity, it's a mirror reflecting the limits of human knowledge. Every unexplained flicker of light, every gravitational anomaly whispers a tantalizing question. What if we're missing something fundamental about how the universe works? What if the answers hidden here could rewrite our cosmic story? This isn't just about distant galaxies, it's about the thrill of discovery, the ache of the unknown, and the humbling reminder that the universe still holds cards it hasn't shown us. So buckle up, because by the time we're done, you'll never look at the night sky the same way again. The journey starts now. One of the most startling discoveries in the Coma Cluster turns everything we know about dark matter on its head, because in some regions it's simply gone. This shouldn't happen. Dark matter, the invisible scaffolding of the cosmos, is supposed to be everywhere, especially in dense galaxy clusters like Coma. Its gravitational pull is what holds these colossal structures together, keeping galaxies from flying apart. But when astronomers mapped the cluster's mass using the bending of light from distant objects, a technique called gravitational lensing, they found eerie gaps where the dark matter signal vanished. It's like looking at a city skyline at night and seeing entire blocks where the lights mysteriously flicker out. So where did it go? One possibility is that violent collisions between galaxies might have slingshotted dark matter out into the cosmic void, scattering it like debris from a cosmic car crash. Another theory suggests we're not seeing it because it's there, just in a form so strange our current tools can't detect it. Some researchers even speculate that dark matter interacts with itself in ways we don't yet understand, clumping or dissolving under conditions unique to the Coma Cluster. But the most unsettling idea, that our models of dark matter might be fundamentally wrong. The implications ripple far beyond this one cluster. If dark matter can disappear or behave unpredictably, it throws into question decades of astrophysics. Entire theories about how galaxies form and how the universe evolved could need rewriting. And yet, this isn't just a problem for scientists, it's a thrilling reminder that the universe still has tricks up its sleeve. Every time we think we've figured it out, places like the Coma Cluster whisper back, "You're missing something." Imagine a galaxy stretched thin like fog, as wide as our Milky Way but glowing with only 1% of its stars. These aren't cosmic mirages, they're ultra-diffuse galaxies, some of the most perplexing residents of the Coma Cluster. They float through space like ghost ships, nearly invisible against the black backdrop of the universe. How can something so massive contain so little light? That's the puzzle astronomers face when studying these enigmatic structures, which defy every expectation of how galaxies should form and survive. Take Dragonfly 44, one of the most famous ultra-diffuse galaxies in Coma. Despite its faint glow, this galaxy weighs as much as the Milky Way, with 99% of its mass hidden in the form of dark matter. It's like finding a balloon the size of a stadium that somehow weighs almost nothing when you pick it up until you realize it's filled with something invisible, something that shouldn't exist in such staggering amounts. Normally, galaxies with so few stars would be ripped apart by the gravitational forces of their neighbors. Yet here they are, intact, as if held together by secrets we can't yet decode. The existence of these galaxies throws a wrench into our models of cosmic evolution. If galaxies form where dark matter clumps together, why do some end up so dim and stretched out? One theory suggests they're failed galaxies, ancient relics that never gathered enough gas to birth stars in abundance. Another proposes they were once normal galaxies, stripped bare by the brutal tides of the Coma Cluster's gravity, leaving behind only their dark matter skeletons. But perhaps the most intriguing idea is that ultra-diffuse galaxies are a cosmic accident, forming in ways we haven't even imagined yet. What makes these ghostly giants even stranger is their resilience. In a cluster as dense and chaotic as Coma, where galaxies frequently collide and merge, ultra-diffuse galaxies somehow avoid destruction. They drift undisturbed, as if the universe has carved out a quiet corner just for them. This isn't just a curiosity, it's a clue. If we can unravel how these galaxies survive, we might uncover hidden rules of cosmic ecology, laws that dictate which galaxies thrive and which fade into the dark. The mystery deepens when we consider their dark matter dominance. In most galaxies, dark matter and visible matter dance in balance, but in ultra-diffuse galaxies, dark matter seems to have taken the lead entirely. This imbalance challenges our understanding of how matter interacts across the universe. Are these galaxies outliers, or are they showing us a side of dark matter we've never seen before? Every observation peels back another layer, revealing just how much we still don't know about the invisible threads weaving the cosmos together. Ultra-diffuse galaxies aren't just oddities, they're windows into the unseen forces shaping our universe. With every discovery, they force us to question what we think we know about galaxy formation, dark matter, and the delicate balance that allows cosmic structures to exist at all. And as telescopes grow more powerful, one thing becomes clear: the Coma Cluster's whispers are getting louder, and they're telling us we've only just begun to listen. Deep within the heart of the Coma Cluster, an invisible giant stretches its arms across millions of light years, a colossal radio halo, pulsing with energy we can't see with our eyes but can hear through the whispers of radio telescopes. This isn't just background noise, it's a roaring chorus of synchrotron radiation, emitted by electrons spiraling at nearly the speed of light through tangled magnetic fields. The sheer scale of this phenomenon is staggering. If our eyes could perceive radio waves, the halo would appear larger than 60 full moons lined up in the sky. Yet despite its breathtaking size, its origins remain one of the cluster's most enduring mysteries. What makes this halo so confounding is the sheer amount of energy required to sustain it. Electrons don't race like this without a cosmic push. Something in the Coma Cluster is acting like a particle accelerator on a scale we can barely comprehend. One leading theory points to the violent dance of galaxies within the cluster. As these galaxies collide and merge, they create shock waves rippling through the thin gas between them, turbulence that could energize particles to extreme speeds. Picture a stormy ocean where crashing waves churn the water into froth, except here, the waves are made of gravity and plasma, and the froth is a sea of high-energy electrons. But there's a problem with this explanation. The halo's radio emission is too smooth, too evenly spread. If galaxy collisions were the sole source, we'd expect patchy, irregular emission, like flickering spotlights in the dark. Instead, the halo glows uniformly, suggesting something else, something older and more pervasive, is at work. Some astronomers argue this could be the fading echo of an ancient cataclysm, perhaps a shock wave from the cluster's formation billions of years ago, still reverberating through the cosmos. Others speculate that the halo is fueled by continuous energy injection from invisible dark matter interactions, a process we've yet to fully grasp. Then there's the puzzle of the magnetic fields. The radio halo's existence implies that the Coma Cluster is threaded with magnetic forces far stronger and more organized than expected. These fields shouldn't survive for long in the chaotic environment of a galaxy cluster where gas motions ought to shred them apart. Yet here they are, not only persisting but shaping the paths of particles across millions of light years. It's like discovering an invisible spiderweb woven so perfectly it defies the very storms that should tear it to pieces. This raises a tantalizing possibility. What if magnetic fields play a far greater role in shaping galaxy clusters than we've ever realized? The implications ripple outward. If we can decode the radio halo's secrets, we might unlock new truths about how energy flows through the universe, how cosmic structures evolve, and even how dark matter interacts with the visible world. Every observation peels back another layer, revealing just how dynamic and how little we understand the space between galaxies truly is. The Coma Cluster's radio halo isn't just a curiosity, it's a cosmic shout in the dark, daring us to listen closer. And as our telescopes grow more sensitive, one thing becomes clear: the universe is still teaching us how to hear. At the heart of the Coma Cluster, a seething ocean of gas burns hotter than the core of most stars, a swirling plasma of hydrogen and helium reaching temperatures of tens of millions of degrees. This gas doesn't glow in visible light. Instead, it screams its presence in X-rays, painting the cluster in strokes of high-energy radiation that baffle astronomers. What's truly startling isn't just the heat, it's the sheer volume. The Coma Cluster holds up to 6 times more of this scorching gas than models predict, as if the universe forgot to turn off a cosmic faucet. So how do we even detect this invisible inferno? X-ray telescopes like Chandra act as our eyes, capturing photons emitted when the gas's electrons are brutally stripped from their atoms and then crash back together. The resulting glow outlines a landscape of violent filaments and bubbles where gas has been stirred by gravitational turmoil, like cream swirling in a cup of cosmic coffee. But here's the puzzle. Clusters this mature should have settled down, their gas cooling and condensing into new stars. Yet Coma's gas remains frenzied, defying the quiet old age expected of such a structure. One explanation points to a history of galactic bar fights. When smaller galaxy groups plunge into the cluster, their gas doesn't go quietly. Like boulders tossed into a pond, these mergers send shockwaves rippling through the existing gas, reheating it over and over. Evidence of this lies in the gas's lumpy distribution, with some regions denser and hotter than others, a fossil record of past collisions. But even this violent past doesn't fully account for the gas's staggering abundance. Where did the extra come from? A darker possibility lurks in the spaces between galaxies. Thin tendrils of gas strung across the cosmic web like dew on a spider's silk might be funneling fresh material into the cluster at a rate we've underestimated. These filaments, nearly invisible to our instruments, could act as hidden pipelines feeding Coma's insatiable appetite. Then there's the role of supermassive black holes. Their outbursts of energy, though powerful, are usually thought to push gas away, but some simulations suggest they might also churn and trap it, like a whirlpool dragging flotsam beneath the surface. The implications are profound. If we're underestimating how much gas clusters can hoard, we might also be misjudging how galaxies evolve within them. Star formation, galaxy growth, even the fate of cosmic structures all depend on the delicate balance of this hot, invisible medium. Coma's gas excess isn't just a local anomaly. It's a challenge to our understanding of how the universe organizes itself on the grandest scales. Every new observation peels back another layer, revealing how much we still have to learn about the fiery heart of galaxy clusters. Among the Coma Cluster's many oddities, some galaxies seem to be breaking the cosmic speed limit, racing through space so fast they shouldn't stay bound to the cluster at all. These aren't just slightly speedy neighbors, they're cosmic renegades moving at thousands of kilometers per second, velocities that defy the gravitational pull of the cluster's visible mass. It's as if someone flung a handful of marbles into the air, only to watch them zip sideways instead of falling back down. Measuring these breakneck speeds isn't simple. Astronomers rely on the Doppler shift, the stretching or compressing of light waves as galaxies move toward or away from us. By analyzing spectral lines from starlight, they can clock each galaxy's velocity with precision. But when they tallied the numbers, something didn't add up. The fastest movers should have escaped the cluster's gravity long ago, unless there's far more mass holding them in place than we can see. This discrepancy points to the cluster's hidden architecture. Either the Coma Cluster is far more massive than its visible galaxies and hot gas suggest packed with unseen dark matter in a lopsided, clumpy distribution, or something else is at play. One radical idea proposes that dark matter isn't just passively tugging on these galaxies, but might interact with itself through unknown forces, creating invisible currents that slingshot galaxies to extreme speeds. Picture a river of dark matter flowing through the cluster, carrying galaxies along like leaves in a cosmic rapids. Another possibility: the cluster's gravitational field isn't smooth but warped by substructures we've yet to map. Dense knots of dark matter or even smaller, dimmer galaxies lurking undetected. These hidden mass concentrations could be acting like gravitational boost pads, kicking passing galaxies to higher speeds. It's akin to rolling a ball across a bumpy table. You'd expect it to slow down, but if the surface is riddled with unseen slopes, the ball might suddenly accelerate in unexpected ways. The implications ripple beyond Coma. If galaxy speeds reveal unaccounted for mass, our entire understanding of cluster formation could need revising. Maybe clusters aren't the orderly, spherical structures we've modeled, but chaotic, asymmetric playgrounds where dark matter sculpts the rules. Every rogue galaxy adds another piece to this puzzle, reminding us that the universe's quiet corners often hold the loudest secrets. And as we peer deeper, one question lingers: what else is moving in the dark just beyond our sight? In a place as crowded as the Coma Cluster, you'd expect galaxies to be bustling stellar nurseries, churning out new stars at a frantic pace. Instead, many of them are cosmic ghost towns, quiet, aging, and eerily devoid of star formation. This isn't just a minor oddity, it's a direct challenge to our understanding of how galaxies evolve. Normally, dense environments like Coma should trigger star birth as gas clouds collide and compress. Yet here, the opposite is happening, and the reason lies in the cluster's brutal gravitational playground. Take NGC 4860, a spiral galaxy caught in the cluster's grip. Observations show its gas, the raw material for new stars, is being violently ripped away as it plows through the cluster's hot intergalactic medium. This process, called ram pressure stripping, acts like a cosmic sandblaster, scouring galaxies of their star-forming fuel. Picture a runner sprinting through a downpour, their clothes soaked and heavy, except here the runner is a galaxy, and the rain is a hurricane of million-degree gas stripping it bare. The result, a galaxy left gas-starved and stagnant, its spiral arms fading into obscurity. But ram pressure isn't the only culprit. The Coma Cluster's sheer gravitational might also trigger a phenomenon known as strangulation. As galaxies fall into the cluster, the surrounding environment prevents fresh gas from reaching them, cutting off their supply like a tightened noose. Without this inflow, galaxies exhaust their reserves over billions of years, turning from vibrant blue spirals into dull, red relics. Hubble Space Telescope images reveal this transition in stark detail. Galaxies like IC 4040, once alive with young stars, now reduced to faint smudges of aging stellar populations. What makes Coma particularly ruthless is the combined efficiency of these mechanisms. In most clusters, galaxies might experience one form of suppression, but here they face an all-out assault. The cluster's dense core acts like a galactic battlefield, where mergers, tidal forces, and gas stripping work in tandem to quench star formation faster than anywhere else we've observed. Even more puzzling, some galaxies show signs of premature quenching, their star formation snuffed out before they've fully entered the cluster, as if the environment's influence reaches farther than we thought possible. Could there be other forces at play? Radio observations hint at another layer to the mystery. Jets from supermassive black holes in the cluster's central galaxies might be pumping energy into the surrounding gas, heating it to temperatures too high for star formation to ignite. It's a cosmic feedback loop. Black holes suppress stars, which in turn limits the fuel feeding the black holes, creating a strange equilibrium that keeps the cluster's galaxies in a state of suspended animation. The implications stretch far beyond Coma. If these processes are more efficient than we've modeled, entire chapters of galaxy evolution might need rewriting. Are we underestimating how quickly dense environments can strangle star formation? And what does this mean for the fate of galaxies in our own cosmic neighborhood? Every quenched galaxy in Coma is a cautionary tale, a glimpse into a future where even the brightest stellar metropolises fade into the dark. Yet, in their silence, they speak volumes, revealing the delicate balance between creation and destruction that shapes the universe. The galaxies of the Coma Cluster aren't scattered randomly like marbles dropped on the floor. They're lining up in eerie, coordinated formations, as if pulled by invisible threads across the cosmos. This isn't just a curious pattern. It's a direct challenge to our assumption that galaxy clusters should be chaotic, unruly places where gravity's dice roll without favor. Instead, astronomers have found galaxies aligning along vast, sweeping arcs, their orientations synchronized over distances that defy easy explanation. It's like walking into a forest and finding every tree leaning in the same direction, their trunks bent by some unseen, pervasive force. How does this happen? One clue lies in the cluster's turbulent past. During Coma's formation, smaller galaxy groups didn't just merge haphazardly. They fell into the growing cluster along cosmic highways, the dense filaments of dark matter that weave the universe's large-scale structure. These filaments act like celestial rivers, channeling galaxies into the cluster with a directional bias that leaves a lasting imprint. Over time, as galaxies streamed in along these same paths, their motions and orientations became subtly aligned, like iron filings organizing themselves along the lines of a magnetic field. The result, a cluster that isn't just a blob of galaxies but a fossil record of its own assembly, preserving the memory of its growth in the way its inhabitants are arranged. But there's more to it than ancient history. The cluster's gravitational tides, the stretching and squeezing forces exerted by its immense mass, may also be at work, slowly twisting galaxies into alignment like hands molding clay. This process, known as tidal torquing, doesn't just affect individual galaxies. It can nudge entire groups toward a shared orientation, creating the large-scale coherence we observe. Imagine 100 compass needles scattered on a table, each jostled by passing magnets until, over time, they all point roughly north. In Coma's case, the magnets are the cluster's gravitational tides, and the needles are galaxies billions of times more massive than our Sun. The wild card in all this, dark matter, not just as a passive scaffold but as an active participant in shaping galaxy alignments. Some simulations suggest dark matter halos. The invisible cocoons surrounding each galaxy might spin in sync with the cosmic web, their angular momentum imprinted by the universe's expansion. If true, this would mean galaxy alignments aren't just superficial trends but deep, fundamental features tied to the birth of structure in the cosmos. It's a humbling thought. The way a galaxy turns today might be a whisper from the first moments after the Big Bang, yet not every galaxy falls in line. Some rebel, their orientations chaotic, their motions unpredictable. This mix of order and chaos is what makes Coma so fascinating. It's not a sterile laboratory, but a dynamic ecosystem where multiple forces vie for dominance. The alignments we see aren't perfect, and that imperfection is itself a clue. It tells us that while large-scale forces set the stage, local interactions, galactic collisions, close encounters, the violent feedback from supermassive black holes add layers of complexity, scrambling the signal like static over a radio transmission. What does this mean for our understanding of the universe? If alignments are common in clusters, they could be a universal signature of how cosmic structures grow, a hidden rulebook for galaxy evolution. Alternatively, Coma's peculiar alignments might make it an outlier, a cosmic oddball that pushes us to question whether we've oversimplified the story. Either way, every aligned galaxy is a breadcrumb leading us deeper into the maze of dark matter, gravity, and the forces that sculpt the universe on scales we're only beginning to grasp. And as telescopes map more clusters in finer detail, one thing is certain: the universe has a flair for symmetry we're just starting to decode. Hidden in the Coma Cluster's depths are galaxies so faint they barely cast a shadow, cosmic phantoms detectable not by their light, but by the way they bend the fabric of space itself. These dark galaxies are among the most elusive objects in the universe, emitting less than 1% of the starlight of a typical galaxy, yet weighing as much as our Milky Way. Their discovery wasn't the result of a direct sighting but a cosmic accident, spotted only when astronomers noticed something peculiar. Background galaxies flickering like candles seen through warped glass, their light stretched and twisted by unseen masses. The culprit, invisible galaxies bending light like lenses made of pure gravity. What makes these dark galaxies so baffling is their sheer emptiness. They should, by all accounts, be bustling with stars, yet scans across every wavelength, from radio to X-ray, reveal almost nothing. It's as if someone took a normal galaxy and erased 99% of its stars, leaving behind only a ghostly imprint of mass. One leading theory suggests these structures are cosmic dead ends, regions where gas gathered but never ignited into stars. Picture a cloud of hydrogen collapsing under its own weight, only to fizzle out in the cold silence of space, like a firework drenched before it could spark. But there's a darker possibility lurking in the data. Some of these galaxies might be almost entirely made of dark matter, with only a sprinkling of stars to betray their existence. Simulations show that in dense environments like the Coma Cluster, dark matter could clump into halos so massive they trap sparse gas, preventing it from condensing into stars. The result, a galaxy that's all skeleton, no flesh, a shadow puppet cast by the invisible hand of dark matter. This would explain why they're so hard to spot. Without stars, they're effectively camouflaged against the black backdrop of space, detectable only when their gravity distorts the light of objects behind them. Yet even this explanation raises new questions. Why don't these dark galaxies follow the same rules as their luminous counterparts? In most of the universe, dark matter and visible matter dance in balance, but here the scales tip violently toward the invisible. Are they relics of a time when the universe was stranger, a throwback to an era when dark matter ruled unchallenged? Or are they victims of the Coma Cluster's harsh environment, stripped of their star-forming gas by the same forces that quench normal galaxies? The implications ripple beyond astronomy textbooks. If dark galaxies are real and common, they could rewrite our understanding of galaxy formation, proving that the universe builds structures in ways we've never imagined. They might even hold clues to the nature of dark matter itself, whether it's cold, warm, or something else entirely. Every flicker of distorted light from these cosmic ghosts is a whisper from the dark, reminding us how much of the universe remains hidden, waiting to be uncovered. And in the Coma Cluster, the whispers are growing louder. If you zoom in on the Coma Cluster, past its giant galaxies and swirling gas, you'll find a swarm of cosmic underdogs, dwarf galaxies, each no bigger than a flicker compared to their massive neighbors. But here's the twist: these tiny galaxies aren't scattered evenly like sprinkles on a cupcake. Instead, they huddle together in bizarre, lopsided clumps, defying every simulation astronomers have run. It's as if the universe played a game of dice with their positions and then cheated. Why does this matter? Because according to our best models, dwarf galaxies should be the ultimate conformists. They're so small and fragile, the cluster's gravity should have yanked them into a smooth, even distribution by now. Instead, they cluster in ragged groups, clinging to each other like survivors on a life raft. Some regions are packed so tightly they resemble mini-clusters within the cluster, while other areas lie eerily empty, a cosmic seesaw that shouldn't exist. One explanation points to the cluster's violent past. When smaller galaxy groups fell into coma, their dwarf galaxies might have been dumped into orbit like passengers tossed from a crashing train. These infalling dwarfs could have stuck together, their mutual gravity resisting the cluster's pull just enough to preserve their clumpy distribution. Evidence for this lies in their odd orbits. Many of these dwarfs move in coordinated streams, like birds flocking against the wind, a telltale sign they arrived together. But there's a darker, more puzzling layer. Some clumps of dwarfs don't trace back to any obvious parent group. They just exist, islands of small galaxies floating in the wrong places. This raises a radical question. Could dark matter be herding them? Simulations suggest the cluster's dark matter isn't a uniform fog but a tangled web of dense knots and filaments. Dwarfs might be getting caught in these invisible thickets, trapped like fireflies in a spider's web. If true, their distribution isn't random. It's a map of the cluster's hidden dark matter skeleton. Then there's the wild card of tidal forces. As dwarfs plunge through the cluster, the gravitational tide stretching and squeezing them like taffy might strip away their stars and gas, leaving behind ultra-faint ghosts. But instead of dispersing evenly, these remnants could be piling up in gravitational eddies, creating the clumps we see. It's a cosmic version of debris collecting in a river's calm spots after a flood. The implications are profound. If dwarf galaxies refuse to play by the rules in coma, it could mean our simulations are missing a critical ingredient, perhaps how dark matter behaves on small scales, or how galaxies interact with their environment over billions of years. Every misplaced clump is a clue, a whisper that the universe's recipe for building clusters is more complex than we've assumed. And in those whispers lies a tantalizing truth: the smallest galaxies might hold the biggest secrets. At the core of the Coma Cluster, something monstrous is firing particle beams into the cosmos with energies that dwarf anything our most powerful colliders could produce. These aren't gentle streams but violent, focused jets, narrow columns of plasma and radiation screaming outward at nearly the speed of light, stretching hundreds of thousands of light years into space. Detected through their telltale gamma ray and radio signatures, these beams defy expectations, not just for their sheer power but for their eerie precision, as if some cosmic artillery is taking aim at the universe itself. How do we even observe such phenomena? The beams announce themselves through synchrotron radiation light emitted when electrons spiral around magnetic field lines at relativistic speeds. Telescopes like the Chandra X-ray Observatory and the Fermi Gamma Ray Space Telescope catch this high-energy scream, painting a picture of particles being accelerated to energies millions of times greater than anything possible on Earth. But the real mystery lies in their origin. While supermassive black holes are the usual suspects, the beams in coma don't behave like typical black hole jets. They're more chaotic, less collimated, and far hotter than models predict, as if the cluster's central black hole is firing wild, unsteady bursts into the void. One theory suggests these beams might be the aftermath of a black hole feeding frenzy. When multiple supermassive black holes merge, a common event in dense clusters, the resulting monster could launch jets in unpredictable directions, like a fire hose flailing under extreme pressure. Alternatively, the beams might not come from one source at all, but from a chorus of smaller black holes, their combined outflows intertwining into a single diffuse roar. This would explain why the emission is so widespread, smeared across the cluster's core like paint thrown against a wall. Then there's the impact. These particle beams don't just vanish into space, they slam into the cluster's already scorching gas, heating it further and carving out vast cavities in the process. X-ray images reveal these voids as dark bubbles in the glowing plasma, regions where the jets have literally blown the gas aside. The energy involved is staggering. A single beam could power a galaxy for millions of years. Yet instead of triggering star formation, this energy does the opposite, keeping the gas too hot to collapse into new stars. It's a cosmic paradox, a force capable of birthing suns, instead leaving behind sterile bubbles, like a wildfire that burns so hot it sterilizes the soil. What makes Coma's beams especially puzzling is their sheer efficiency. In most clusters, black hole jets dissipate quickly, their energy absorbed by the surrounding medium. Here, the beams seem to punch through with unnatural ease, as if the cluster's gas is thinner or more permeable than it should be. Some researchers speculate this could be due to pre-existing turbulence in the gas, a froth of motion left over from ancient mergers creating channels that let the beams travel farther. Others wonder if the beams are being refueled along the way, perhaps by interactions with dark matter or unseen magnetic fields. The implications ripple far beyond Coma. If black hole beams can shape their environments this dramatically, they might be key players in how galaxy clusters evolve, regulating star formation and gas distribution on cosmic scales. And if their energies routinely surpass predictions, we might need to revisit our models of how black holes convert infalling matter into radiation. Every detection peels back another layer, revealing a universe more dynamic and violent than we'd imagined, one where invisible forces sculpt the cosmos with beams of pure energy. And in the Coma Cluster, those beams are writing their message across the sky, if only we can learn to read it. Scattered throughout the Coma Cluster, invisible to the naked eye but glowing fiercely in ultraviolet light, float vast clouds of ionized gas, orphans of the cosmos, drifting without any galaxy to call home. These aren't just wisps of leftover material, they're colossal structures, some spanning tens of thousands of light years, their atoms stripped of electrons and shimmering like neon signs in the cosmic dark. What makes them so unsettling isn't just their size or their solitude, but their very existence. Gas this hot and energized shouldn't be able to survive untethered in the harsh environment of a galaxy cluster. Yet here they are, glowing defiantly, as if nature forgot to write them out of the script. The discovery of these ghostly clouds came not from traditional telescopes, but from instruments sensitive to the faint ultraviolet glow of ionized oxygen. When astronomers trained the Hubble Space Telescope on Coma, they caught spectral signatures of doubly ionized oxygen, atoms so thoroughly battered by energy they've lost 2 electrons. This ultraviolet fingerprint revealed gas heated to tens of thousands of degrees, floating in regions where no galaxies or stars could explain the heat source. It's like stumbling upon a forest of smoldering embers long after the campfire has burned out, with no sign of what sparked them. Their chemical composition only deepens the riddle. These clouds are rich in heavy elements, oxygen, nitrogen, even traces of iron materials forged in the hearts of stars and typically found deep within galaxies. So how did they end up adrift in the void? One leading theory points to galactic violence. When galaxies collide or pass too close to the cluster's center, gravitational tides can rip them apart, scattering their innards like confetti. The gas, torn free and heated by shock waves, might then linger as a ghostly echo of the catastrophe. But there's another, more dramatic possibility. These clouds could be the fallout from active galactic nuclei, the supermassive black holes at the hearts of galaxies. When these black holes feed, they don't just swallow matter, they spit it back out in furious winds and jets, ejecting material at speeds high enough to escape their host galaxies entirely. Over millions of years, this ejected gas could cool just enough to form the ionized clouds we see, like smoke rings blown into space by a celestial pipe smoker. Then there's the puzzle of their survival. The Coma Cluster's intergalactic medium is a brutal place filled with scorching plasma and turbulent magnetic fields. Normally, isolated gas clouds should dissipate quickly, either evaporating into the surrounding heat or condensing into new stars. Yet these clouds persist, their edges sharper and more defined than models predict. Some researchers speculate they might be encased in faint, undetected halos of dark matter, their gravitational embrace keeping the gas from scattering. Others suggest magnetic fields could be acting like invisible bottles, trapping the ionized material in place against all odds. The implications ripple beyond Coma. If such clouds are common, they could represent a hidden phase of galactic evolution, a way for galaxies to shed material and chemically enrich their surroundings without fireworks. They might even serve as fuel depots for future star formation, reservoirs of heavy elements waiting to be tapped by passing galaxies. But perhaps most intriguing is what they tell us about the cluster's history. Every cloud is a fossil, a snapshot of some violent event that occurred billions of years ago, its story written in the glow of ionized atoms. As telescopes grow more sensitive, these ghostly clouds may finally give up their secrets. For now, they drift in silence, luminous reminders of how much we still don't understand about the chaos and beauty of galaxy clusters, and how even the emptiest corners of space can hold the most surprising stories. Deep in the heart of the Coma Cluster, astronomers are staring at a cosmic accounting error, one where the books don't balance, and the missing sum could rewrite our understanding of ordinary matter. According to the universe's ledger, there should be far more baryonic matter, the protons, neutrons, and electrons that make up stars, planets, and us than we can currently detect. Where did it all go? This isn't just a case of misplaced cosmic change. It's a gaping hole in our inventory of the universe's building blocks, and the Coma Cluster is ground zero for the mystery. For decades, scientists have calculated the expected baryonic matter in clusters like Coma by studying the cosmic microwave background, the afterglow of the Big Bang. These measurements tell us how much ordinary matter the universe should have. Yet when they tally what's visible stars, glowing gas, dust, the numbers fall shockingly short. In Coma, up to half the predicted baryons are unaccounted for, as if the universe stashed them in a hidden vault. The question isn't just academic. If we can't find this matter, we might be missing a fundamental piece of how galaxies and clusters form. So where could it be hiding? One leading suspect is the warm hot intergalactic medium, or WIM, a theorized web of diffuse, superheated gas threading the cosmos. This isn't the scorching plasma of cluster centers or the icy hydrogen of deep space, but something in between. Gas heated to hundreds of thousands of degrees, too hot to form stars but too cool to glow brightly in X-rays. Detecting WIM is like trying to spot a ghost in a fog bank. Its signals are faint and easily drowned out by brighter sources. Yet hints of it have surfaced in the spectra of distant quasars, their light subtly dimmed by intervening WIM absorption lines, like finding fingerprints on a window we didn't know was there. The trouble is, even if WIM exists, it's unlikely to account for all the missing matter. That sent scientists searching for other hiding spots. One bold idea suggests vast, undetected filaments of gas might stretch between galaxies, too thin to see but collectively massive. Picture the cluster as a towering city, with gas filaments acting like underground pipes, essential infrastructure hidden from view. These filaments could have formed during the cluster's assembly, left behind as matter funneled into galaxies, their faint glow lost in the cosmic background noise. Another possibility, the missing baryons might be lurking in plain sight, disguised as something else. Low-energy gas cooled over billions of years could have condensed into faint, cold clouds that evade detection. Or perhaps the matter has been pushed out to the cluster's outskirts by galactic winds or black hole jets, spread so thin it's effectively invisible. There's even a chance it's trapped in exotic forms condensed into rogue planets, floating black holes, or other dark, compact objects we've yet to imagine. The stakes couldn't be higher. If baryonic matter is hiding in these elusive states, it means our tools for observing the universe are still woefully incomplete. It would be like trying to study Earth's oceans by only looking at the waves, missing the entire ecosystem beneath. Worse, if we've misjudged how matter distributes itself in clusters, our models of cosmic evolution, how galaxies grow, how structures merge, might be built on shaky foundations. Yet for all the uncertainty, the hunt for missing baryons is also a story of scientific ingenuity. New telescopes, like the upcoming Athena X-ray Observatory, are being designed specifically to probe these shadows, while advanced simulations trace the possible fates of ejected gas. Every flicker of unexplained absorption, every faint signal in the noise, brings us closer to balancing the books. And when we do, the Coma Cluster won't just be a collection of unsolved riddles, it'll be the key that unlocked one of the universe's best-kept secrets. Until then, the missing matter remains a silent challenge, a reminder that even the most ordinary ingredients of the cosmos can still surprise us. At the center of many galaxies in the Coma Cluster, something impossible is lurking: supermassive black holes so large they defy everything we know about how these cosmic giants should grow. These aren't just big black holes, they're overmassive, weighing in at up to 10 times more than predicted based on their host galaxy's size. It's as if every skyscraper in a city had a foundation built for a 10-story building, only to find out the basement stretched halfway to the Earth's core. The discovery has sent shockwaves through astrophysics, forcing scientists to rethink the fundamental relationship between galaxies and the monsters at their hearts. Measuring these gravitational behemoths wasn't simple. Astronomers relied on two key techniques: tracking the dizzying orbits of stars near the galaxy's cores and analyzing the way gas swirls like water draining a cosmic bathtub around the black hole's event horizons. In Coma, the results were staggering. Galaxy NGC 4889, for example, hosts a black hole weighing nearly 21 billion suns, a figure so enormous it shouldn't exist in a galaxy of its modest luminosity. Normally, black hole mass scales neatly with the bulge of stars at a galaxy's center, but here the rules seem broken. So how did these black holes get so outrageously large? One possibility is a frenzy of galactic mergers. The Coma Cluster's crowded environment is like a cosmic mosh pit where galaxies frequently collide and merge. Each collision funnels gas and stars toward the central black holes, allowing them to feast and grow far beyond typical limits. Imagine two competing restaurants merging over and over. Eventually, you'd end up with a single, grotesquely oversized kitchen. But even this explanation falls short. Simulations show merger-driven growth shouldn't produce black holes this disproportionate to their galaxies unless the mergers were exceptionally gas-rich, something Coma's aging stellar population doesn't support. Another theory points to an unseen phase of hypergrowth in the early universe. Perhaps these black holes were seeded by direct collapse, a rare process where massive gas clouds in the infant universe bypassed star formation entirely, collapsing straight into black holes weighing thousands of suns from birth. These primordial titans would have had a head start, gorging on gas long before their host galaxies took shape. Supporting this idea, some of Coma's overmassive black holes show signs of extreme antiquity, their growth spurts concentrated in the universe's first few billion years. Yet the puzzle deepens when we consider feedback. Supermassive black holes are supposed to regulate their own growth. Their ferocious radiation and jets should blow away surrounding gas, cutting off their food supply. But in Coma, something appears to have circumvented this balance. One provocative idea suggests the cluster's dense environment stifled feedback, trapping gas so efficiently that black holes could keep eating long after they should have pushed their plates away. Picture a diner whose exhaust fan breaks, letting the kitchen fill with steam, except here, the steam is energy and the kitchen is a black hole's feeding zone. The implications rewrite galactic evolution. If black holes can grow disproportionately large, they might dominate their galaxy's fate earlier than we thought, quenching star formation prematurely or distorting entire galactic structures with their gravity. It also raises a haunting question: how many other clusters harbor these cosmic rule breakers, hiding in plain sight? The Coma Cluster's overmassive black holes aren't just oddities, they're a challenge to our understanding of how the universe builds its largest structures. And as we peer deeper into their abysses, one thing becomes clear: the rules we thought governed black holes might just be suggestions. Gravity is supposed to be the universe's most reliable artist, always sketching the same predictable curves around massive objects. But in the Coma Cluster, its brushstrokes go rogue. Here, light from distant galaxies bends in ways that shouldn't be possible, warping around invisible masses as if space itself has secrets to keep. This is gravitational lensing at its most baffling, a cosmic funhouse mirror where the reflections don't match the objects in front of them. The principle seems simple enough. According to Einstein, massive objects warp spacetime, causing light to curve around them like a car navigating a highway's bend. By measuring this distortion, astronomers can map the cluster's mass, both visible stars and gas, plus the invisible dark matter scaffolding. But in Coma, the maps don't line up. Some regions show extreme lensing with almost no visible mass to explain it, while other areas packed with galaxies produce oddly weak distortions. It's like stepping on a scale that claims you weigh 300 pounds, while your reflection in the mirror shows a 100-pound frame. One glaring anomaly lies near the cluster's core, where a patch of sky bends background light into razor-sharp arcs, a signature of something enormously dense. Yet scans reveal only a wispy haze of hot gas and a handful of dim galaxies, far too lightweight to account for the effect. The math suggests there's 30 times more mass here than we can see. So what's hiding in the shadows? One tantalizing possibility involves dark matter clumps, dense knots of invisible particles drifting like icebergs through the cluster. These clumps wouldn't glow or absorb light, but their gravity would sculpt spacetime just like visible matter. Simulations suggest such clumps could form during the cluster's violent growth, as smaller groups of galaxies merged and their dark matter halos fragmented. Yet even dark matter might not fully explain the discrepancies. Some lensing patterns hint at structures far more exotic: cosmic strings, hypothetical defects in spacetime left over from the Big Bang, or even primordial black holes forged in the universe's first seconds. These relics would warp light unpredictably, creating lensing signatures unlike anything dark matter alone could produce. Then there's the wild card of modified gravity, the controversial idea that Einstein's equations might need tweaking in extreme environments like galaxy clusters. If correct, the lensing anomalies wouldn't point to missing mass at all, but to gaps in our understanding of gravity itself. The stakes immense. Gravitational lensing is one of our primary tools for mapping the cosmos's hidden architecture. If its signals can't be trusted, our entire model of cosmic structure, from galaxy formation to the universe's expansion, might rest on shaky foundations. Every anomalous bend in Coma's light is a challenge, a dare to look deeper and question harder. And until we solve these cosmic mismatches, one thing is certain: the universe's most reliable artist might just be painting in invisible ink. In the blistering heat of the Coma Cluster's core, where temperatures soar to tens of millions of degrees, astronomers have stumbled upon something that shouldn't exist: delicate threads of cold gas, weaving through the inferno like frost creeping across a furnace. These filaments, some stretching over 50,000 light-years, are cosmic contradictions, pockets of gas chilling at just tens of degrees above absolute zero, surviving in an environment where everything should be vaporized. Their discovery wasn't just surprising, it was like finding ice cubes floating in lava, defying every law of thermodynamics we thought we understood. Spotting these filaments required a cosmic detective's toolkit. While the cluster's scorching plasma glows fiercely in X-rays, the cold gas reveals itself through radio waves, specifically the faint emissions of carbon monoxide molecules. Telescopes like ALMA and the Green Bank telescope picked up these whispers, mapping structures so fragile they'd vanish if exposed to the surrounding heat unprotected. The filaments aren't just cold, they're organized, with some forming intricate braids or feathery tendrils, as if sculpted by unseen hands. How do they endure in this cosmic pressure cooker? One clue lies in their magnetic armor. Simulations suggest these filaments might be wrapped in powerful magnetic fields, acting like insulating blankets that shield the gas from the surrounding plasma. Picture a submarine diving into the Mariana Trench. Its hull withstands crushing pressure because of careful engineering. The cold filaments might rely on a similar principle, with magnetic hulls keeping the chaos at bay. Another theory points to rapid cooling. Turbulence in the cluster's gas could create localized pockets where energy dissipates suddenly, like steam condensing into water droplets, allowing the gas to chill faster than the environment can reheat it. But the real mystery isn't just their survival, it's their origin. Some filaments trace back to the cluster's galaxies, likely stripped away by gravitational tides or ram pressure. Others, though, dangle in empty space, untethered to any visible source. These rogue strands might be relics of ancient cosmic weather, leftovers from a time when the cluster was little more than a swirling storm of gas and dark matter. Alternatively, they could be fuel lines, part of a hidden network funneling gas from the cluster's outskirts to its core, a cosmic plumbing system we've only just begun to glimpse. The implications are staggering. If cold filaments are common, they could rewrite our understanding of how galaxy clusters evolve. They might serve as nurseries for future star formation, oases in the desert where gas can quietly coalesce. Or they could be the universe's recycling centers, gathering material ejected by dying stars and black holes, ready to be repurposed. Every filament is a clue, a frozen whisper from a universe that's far more nuanced than we ever imagined. And in the Coma Cluster, these icy threads are weaving a story we're only just learning to read. In the heart of the Coma Cluster, where chaos should reign supreme, astronomers have stumbled upon a cosmic paradox, unnerving silence. Galaxy clusters this massive typically roar with violence at their cores, supermassive black holes belching jets of plasma, shockwaves rippling through scorching gas, and galaxies colliding in spectacular mergers. Yet Coma's center hums with unexpected tranquility, like the eye of a storm that forgot to rage. This eerie calm isn't just puzzling, it's a direct challenge to everything we thought we knew about how clusters evolve. Take the Perseus cluster, Coma's cosmic cousin, for comparison. There, the central galaxy NGC 1277 hosts a black hole so ravenous, its outbursts carve gargantuan bubbles in the surrounding gas, visible in X-rays like scars across the sky. These eruptions release energy equivalent to 100 million supernovae, stirring the cluster's core into a perpetual maelstrom. Yet in Coma, despite hosting two equally monstrous central galaxies, NGC 4874 and NGC 4889, the scene is startlingly subdued. Jet activity is sparse, gas motions are oddly orderly, and the temperature profile lacks the wild fluctuations seen elsewhere. It's as if someone flipped a cosmic switch, muting the violence. Why does this defy expectations? Clusters like Coma are thought to grow by devouring smaller galaxy groups, a process that should dump fresh fuel, gas and stars onto their central black holes, triggering explosive feedback. The resulting energy prevents the cluster's gas from cooling and forming stars, maintaining equilibrium. But in coma, this cycle appears broken. One possibility is timing. We might be catching the cluster in a rare lull between feeding frenzies, like a predator digesting its meal before the next hunt. Supporting this, some simulations suggest clusters oscillate between states of calm and chaos over billions of years, with coma currently in the quiet phase of its cycle. But there's a darker twist. The cluster's two central galaxies orbit each other in a slow, gravitational dance. They're black holes separated by just tens of thousands of light years. Normally, such a close pairing should spark fireworks, tidal forces ripping gas clouds apart, fueling competing jets. Yet here, both black holes seem strangely dormant. One explanation: they've already gorged on most available gas, starving themselves into quiescence. Another theory proposes their mutual gravity has flung nearby gas into chaotic orbits, preventing it from falling into either black hole's grasp. Picture two lions circling the same prey, each waiting for the other to strike while the meal slips away untouched. The implications ripple far beyond coma. If massive clusters can switch off their engines this decisively, it suggests our models of black hole feedback, a cornerstone of galaxy evolution, might be incomplete. Perhaps feedback isn't just about energy output but timing and geometry, with some clusters developing off switches we don't yet understand. Alternatively, coma's quiet core might hint at an evolutionary endpoint, a fate awaiting all clusters as they exhaust their fuel and settle into old age. Then there's the wild card of dark matter. Some theories suggest the cluster's invisible halo might be unusually smooth or evenly distributed, damping the turbulence that typically stirs up activity. It's like comparing a pot of water on a roaring flame to one on a simmer, the same ingredients, but radically different outcomes based on hidden variables. Whatever the cause, coma's silence speaks volumes. It reminds us that even the most violent corners of the universe have rhythms we're still deciphering, and that sometimes the absence of chaos is the most profound mystery of all. Buried within the coma cluster's scorching X-ray glow lie cosmic voids so vast, they could swallow our Milky Way whole, gigantic cavities carved into the searing plasma, each stretching up to 50,000 light-years across. These aren't random bubbles but precise, symmetrical structures, their edges crisp as if sliced by an invisible knife. When astronomers first spotted them in Chandra X-ray observatory data, the discovery sent shockwaves through the astrophysics community, not just because of their size, but because they defied the laws of cosmic decay. In most galaxy clusters, such cavities fade within 100 million years, swallowed by the surrounding turbulence. Yet in coma, these voids have persisted for nearly 500 million years, lingering like ghosts in a storm. Mapping these voids was no small feat. The hot gas filling the coma cluster emits X-rays at energies around 1 kiloelectronvolt, roughly the same as a dental X-ray, but originating from gas heated to tens of millions of degrees. By analyzing subtle dips in this emission, astronomers trace the cavity's outlines, revealing paired structures flanking the cluster's core like cosmic footprints. Their symmetry points to an explosive origin, jets of high-energy particles screaming outward from a supermassive black hole at nearly light speed, bulldozing the gas aside like snowplows clearing a path. The energy required to punch these holes is staggering, equivalent to 1 trillion supernova detonating in unison. What makes coma's cavities truly baffling is their endurance. In younger clusters, similar structures are quickly erased as the surrounding gas rushes back in, like waves smoothing over footprints on a beach. But in coma, the voids remain pristine, their edges still sharp after eons. One explanation lies in the cluster's unusual gas dynamics. Unlike younger clusters where gas swirls chaotically, coma's central regions are eerily calm, a quirk that might allow the cavities to persist undisturbed. Think of blowing bubbles in a glass of soda versus a glass of honey. The thicker, more viscous environment resists collapse, Here, the honey is the cluster's old, sedimented gas, moving so sluggishly that even billion-year-old cavities stay intact. Another clue comes from the cavities' sheer scale. Their size suggests the black hole that created them didn't just hiccup, it unleashed a sustained apocalyptic belch. This aligns with theories that Coma's central galaxies once hosted hyperactive quasars, their black holes gorging on immense gas reserves before abruptly shutting off. The cavities, then, would be fossils of that ancient frenzy, preserved in the cluster's amber-like gas. But there's a catch. No known black hole outburst should last long enough to carve voids this large. Unless perhaps the jets were refueled by something we've yet to detect, like streams of dark matter falling into the black hole, providing a slow-burning fuse for the explosion. The implications ripple far beyond Coma. If cavities can survive this long, they might serve as cosmic pollen, carrying heavy elements and magnetic fields into the cluster's outskirts, seeding future star formation. They could also explain why some clusters, like Coma, have cores that are oddly devoid of young stars. Their black holes might have blasted away the gas needed to form them. Every cavity is a time capsule, preserving a record of the cluster's most violent moments. And as we peer deeper into these X-ray shadows, one thing becomes clear: the universe doesn't just erase its past. It leaves scars. Among the blazing rivers of gas in the Coma cluster lies an unexpected trove of cosmic treasure, heavy elements like iron, oxygen, and neon scattered through the plasma in amounts that defy expectations. This isn't just a sprinkle of stardust, it's a full-blown metallicity overabundance, with some regions containing up to half the iron content of our Sun, despite being billions of years older. For astronomers, this is like finding a pristine medieval sword in a Stone Age dig site, an artifact that shouldn't belong, hinting at a forgotten epoch of cosmic violence and splendor. The metal's origins trace back to the deaths of massive stars. When these stars explode as supernova, they forge heavy elements in their final moments and blast them into space. But here's the puzzle. In a cluster as ancient as Coma, most star formation should have fizzled out eons ago, leaving little fuel for new supernova. Yet the gas isn't just metal-rich, it's uniformly enriched, as if someone stirred a giant vat of cosmic soup until every drop glittered with stardust. This even distribution contradicts models where metals should clump near their source galaxies, not disperse evenly across millions of light years. One explanation points to galactic winds, hurricane-like outflows powered by countless supernova detonating in unison during the cluster's youth. Imagine a galactic fireworks show so intense, the collective shockwaves blew heavy elements clear out of their home galaxies, seeding the intergalactic medium like pollen scattered by a storm. Supporting this, computer simulations show that early starbursts could have flooded Coma with metals, with turbulence and gravitational tides later mixing them thoroughly. But there's a twist. The sheer volume of metals suggests star formation in Coma's past was far more frenzied than we've accounted for. Some galaxies might have operated as cosmic factories, churning out stars at rates dwarfing even the Milky Way's busiest eras. Their remains, now faded into dim ghosts, would have left behind this elemental smog as their only epitaph. Alternatively, the cluster's violent merger history could have crushed galaxies together, triggering waves of star formation and subsequent supernova that dumped metals into the gas like ore into a crucible. Then there's the role of black holes. Active galactic nuclei spewing jets and winds might have acted as cosmic blenders, shredding gas clouds and dispersing metals farther than supernova alone could manage. It's a messy process, like tossing flour into a fan, but over billions of years, even chaotic forces can create surprising uniformity. The implications stretch beyond Coma. If metal enrichment is this efficient, our models of how elements spread through the cosmos essential for understanding planet formation, and even the chemistry of life might need recalibrating. Every atom of iron in that distant gas is a clue, a remnant of stars that lived fast, died young, and left the universe permanently changed, and in their ashes we're just beginning to read the story. Among the bustling galactic metropolis of the Coma Cluster, some residents have been caught in the act of cosmic escape, galaxies hurtling outward at breakneck speeds, tearing through space as if flung by an unseen slingshot. These aren't just fast movers, they're full-blown fugitives racing toward the cluster's outskirts at velocities exceeding 2,000 kilometers per second, fast enough to eventually break free from Coma's gravitational grip entirely. Their trajectories trace wild arcs across the sky, like sparks flying from a grinding wheel, each one a testament to the violent forces churning beneath the cluster's seemingly orderly surface. Tracking these runaway galaxies wasn't easy. Astronomers had to separate their motion from the cluster's overall churn, like picking out individual sprinting ants in a swarming colony. By measuring redshift shifts in their starlight and comparing their positions over decades, researchers pieced together their paths. Some shot outward like bullets from the cluster's core, while others skimmed perilously close to massive galaxies before being catapulted away, their courses bent by gravitational slingshots. The most extreme example, a spiral galaxy designated G114, now fleeing the cluster at nearly 3,000 kilometers per second, its spiral arms stretched and distorted by the forces that expelled it. What could launch an entire galaxy into exile? The prime suspect is the chaotic dance of supermassive black holes. When two galaxies merge, their central black holes eventually spiral together, and if a third interloper joins the fray, the complex gravitational interplay can eject one of them, and sometimes its host galaxy, at tremendous speeds. Picture a game of cosmic pinball where galaxies ricochet off one another, the losers flung into the void. But black holes aren't the only culprits. The cumulative gravitational kicks from multiple close encounters with other galaxies can also build up momentum, like a snowball rolling downhill, until the galaxy is hurled clear of the cluster's grasp. The implications are profound. Runaway galaxies serve as cosmic speedometers, letting us measure the cluster's gravitational potential in ways traditional methods can't. Their existence hints at hidden substructures, clumps of dark matter or unseen dwarf galaxies that might have nudged them onto their wild paths. Some models even suggest these escapees could be tracers of ancient cluster mergers, their trajectories preserving the memory of collisions that occurred billions of years ago. Yet the biggest surprise isn't that galaxies get ejected, it's how many are fleeing. Coma hosts an unusually high number of runaways compared to other clusters, a clue that its core might be far more turbulent than we thought. This gravitational frenzy could explain other mysteries too, like the cluster's missing dark matter or its lopsided gas distribution. Every escaping galaxy is a breadcrumb leading us closer to understanding the invisible forces shaping the universe's most massive structures. And as these renegades streak toward the void, they carry a warning. The Coma Cluster isn't just a static snapshot of cosmic evolution. It's a battlefield where galaxies are born, broken, and banished, and where the rules of engagement are still being written. One of the most unsettling debates in modern cosmology hides in plain sight within the Coma Cluster, a disagreement so fundamental it threatens to unravel our understanding of cosmic expansion itself. At the heart of the conflict lies the Hubble constant, the number that describes how fast the universe is stretching apart. For decades, astronomers assumed this value was universal, a fixed speed limit etched into the fabric of spacetime. But when they measured it using different methods, the numbers refused to agree, and the Coma Cluster has become ground zero for this cosmic contradiction, where the very laws governing the universe seem to shift depending on how you look at them. The first method relies on the cosmic distance ladder, a step-by-step approach using pulsating stars called cepheids and cataclysmic supernova as mile markers. By tracking their brightness and redshifts, scientists can calculate expansion rates with precision. When applied to galaxies in coma, This approach consistently yields a Hubble constant around 73 kilometers per second per megaparsec. But here's where things get weird. Another technique studying the afterglow of the Big Bang, the cosmic microwave background, predicts a slower expansion closer to 67. Initially dismissed as measurement error, the gap has only widened with better data, reaching a staggering 5 sigma discrepancy. That's not just noise, it's a chasm in our understanding. Coma Cluster observations amplify the tension because they offer a third, independent check. Here, astronomers use the Sunyaev-Zeldovich effect, a subtle distortion in the cosmic microwave background caused by hot cluster gas, to gauge distances. This method sidesteps the distance ladder entirely, yet when applied to Coma, it stubbornly sides with the higher, local universe measurements. It's as if the cluster exists in a pocket of space where expansion runs faster than the cosmic average, a notion that defies the bedrock principle that the universe should look broadly the same in all directions. What could explain this rift? One possibility is that dark energy, the mysterious force accelerating cosmic expansion, isn't constant as we've assumed. Maybe it grows stronger over time or varies across regions, subtly tweaking the Hubble constant in different locales. Alternatively, the Coma Cluster might sit in a local void or overdensity, a cosmic pothole or hill that skews our measurements. But even these fixes feel unsatisfying. The scale of the discrepancy demands something more radical. Some theorists now float ideas like undiscovered particles, modifications to gravity, or even a late time transition in the universe's expansion rate, physics beyond Einstein's relativity. The implications are tectonic. If the Hubble constant truly varies, it means our cosmic timeline, the age of the universe, the fate of galaxies, the very narrative of existence, might need rewriting. Coma's role in this drama isn't incidental. Its sheer mass and proximity make it a natural laboratory, a place where local and global measurements collide with undeniable clarity. Every new observation peels back another layer, revealing not just flaws in our tools but potential cracks in the foundation of cosmology itself. And until this puzzle is solved, one unsettling truth remains: the universe's speed limit might not be as constant as we thought. In the chaos of the Coma Cluster, where galaxies are stripped, stretched, and shattered, one cosmic survivor defies the odds: NGC 4921. A spiral galaxy spinning gracefully against all expectations. While its neighbors have long since been crushed into featureless blobs by the cluster's relentless gravity, this stubborn holdout clings to its delicate spiral arms like a dancer refusing to leave the stage. But this isn't just any spiral galaxy. It's a ghostly version of the Milky Way, its arms so faint they barely glow, its star formation so sluggish it's practically in hibernation. How has it endured where others fell apart? The answer lies in a delicate dance of timing, luck, and cosmic armor. First, consider the violence it's up against. The Coma Cluster's core is a galactic demolition derby, where galaxies collide at thousands of kilometers per second and interstellar gas is ripped away by scorching plasma. Most spirals that wander in are shredded within a billion years, their gas stolen, their stars scattered, their structures pummeled into shapeless ellipses. Yet NGC 4921 remains unmistakably a spiral. Its arms, though wispy, still trace that iconic pinwheel pattern. The secret: distance. This galaxy orbits far enough from the cluster's chaotic center to avoid the worst gravitational assaults, like a kayaker skirting the edge of a whirlpool. But survival isn't just about location, it's about preparation. NGC 4921 is what astronomers call an anemic spiral, its gas reserves already depleted before it entered the cluster's kill zone. Unlike gas-rich galaxies that light up with new stars as they fall inward, this one arrived lean, its star-forming fuel mostly spent. That might sound like a weakness, but in Coma's brutal environment, it's a superpower. With little gas left to strip, the cluster's ram pressure, the force that scours galaxies clean, has almost nothing to grab onto. It's like trying to blow out a candle that's already burned down to the wick. Then there's the matter of its faint arms. Unlike the Milky Way's bold, star-studded spirals, NGC 4921's are barely there, a sketch where others are oil paintings. This isn't just a stylistic quirk, it's a survival trait. The arms' low density means they're less vulnerable to tidal forces, the gravitational stretching that tears structure apart. Think of it as the difference between a rigid sheet of ice and a loose net. When the cosmic tides pull, the net simply bends, yet the galaxy isn't entirely unscathed. Observations reveal subtle signs of disturbance, a warp here, a displaced star cluster there, hints that even this survivor isn't immune to the cluster's grip. Its days as a spiral may be numbered. Some simulations suggest it's in a slow-motion transformation, destined to become a lenticular galaxy, a blurry halfway point between spiral and elliptical. But for now, it stands as a rare window into what most clusters lost long ago, the fragile beauty of a spiral galaxy, aging but unbroken, in the last place you'd expect to find one. What makes NGC 4921 truly extraordinary isn't just its resilience, it's the questions it forces us to ask. Are there others like it hiding in plain sight? Could its survival strategy hint at ways galaxies in less hostile environments might evolve? Every observation of this cosmic holdout chips away at our assumptions, proving that even in the universe's most violent neighborhoods, exceptions don't just defy the rules, they rewrite them. Buried within the gravitational weave of the Coma Cluster are phantom landmarks, vast, invisible structures that tug on galaxies and bend light, yet leave no trace in telescopes. These dark substructures, towering clumps of matter that outweigh entire galaxies, are the cosmic equivalent of footsteps in the dark. We can't see them, but their imprint is everywhere. Astronomers first stumbled upon their existence not by sight, but by math discrepancies in how galaxies move within the cluster that couldn't be explained by visible mass alone. Some galaxies orbit as if tethered to unseen anchors, their paths too tight, too fast for the gravity of nearby stars and gas to account for. Others drift in synchronized streams, like leaves caught in the same invisible current, hinting at massive but hidden scaffolds guiding their motion. The most compelling evidence comes from gravitational lensing, the subtle warping of light from distant galaxies as it skirts these unseen masses. In certain regions, the lensing effect is stronger than the visible matter can produce, betraying the presence of dark knots with up to 10 times the heft of the Milky Way. Yet when telescopes scour these areas, they find nothing but empty space. It's like stepping on a scale and watching the numbers jump, only to look down and see no one standing there. What could these dark substructures be? One unsettling possibility is that they're failed galaxies, clumps of dark matter that gathered in the early universe but never attracted enough gas to birth stars. Picture a cosmic construction site abandoned mid-project. Its steel beams here, dark matter erected but never clad in walls or windows, stars and gas. These dark halos could have formed alongside normal galaxies but remained barren, their potential forever unfulfilled. Alternatively, they might be remnants of galactic cannibalism. When smaller galaxy groups merge into clusters like Coma, their dark matter halos don't blend smoothly. They fragment into smaller subhalos that orbit like ghosts of the original structures. Over time, tidal forces strip away their outer layers, leaving behind dense, dark cores, cosmic fossils of ancient collisions. Simulations suggest the Coma Cluster should be littered with thousands of these fragments, yet we've only detected the most massive ones, raising questions about whether our models underestimate how efficiently dark matter resists disruption. The wild card, these substructures might not be entirely dark. Some could harbor ultra-faint galaxies, so dim they evade detection. Others might contain rogue black holes or exotic particles that interact in ways we've yet to imagine. Every unexplained lensing signal, every aberrant galactic orbit, is a breadcrumb leading us deeper into the dark and closer to answers that could reshape our understanding of how the universe builds its largest structures. Until then, these unseen giants remain both a puzzle and a promise, proof that the cosmos still keeps its deepest secrets hidden in plain sight. On the fringes of the Coma Cluster, where galaxies thin out and the void begins, a faint but unmistakable scar etches across the radio sky, a colossal arc of synchrotron radiation stretching nearly 2 million light-years, visible only to the most sensitive radio telescopes. This is the Coma relic, a ghostly afterimage of violence on a scale we can scarcely comprehend. Unlike the smooth radio halo at the cluster's heart, the relic is jagged, filamentary, almost claw-like in structure, its brightness flickering unevenly across its vast expanse. What makes it truly extraordinary isn't just its size or its distance from the cluster's core, but its staggering energy. The electrons spiraling through its magnetic fields radiate with an intensity that rivals some of the brightest objects in the universe, yet their source remains a mystery. Relics like these are thought to be the cosmic equivalent of sonic booms, shock waves from cataclysmic collisions between galaxy clusters, traveling outward at thousands of kilometers per second. When two clusters merge, their dark matter halos and hot gas clouds slam together, creating ripples of compressed plasma that accelerate particles to near light speeds. These particles then emit radio waves as they spiral around magnetic field lines, painting the aftermath of the collision in strokes of invisible light. But the Coma relic defies expectations. Most relics appear as faint, diffuse smudges. This one is razor-sharp, with intricate substructure suggesting multiple shock fronts piled atop one another, like the wake of a ship crashing through successive waves. One clue to its origin lies in its position. The relic hugs the cluster's outskirts like a shell, aligned perpendicular to the axis connecting Coma to its neighboring cluster, Abell 1367. This geometry hints at an ancient collision between the two, a gravitational pileup so violent it sent shock waves reverberating through the intergalactic medium. Simulations show such an event could have occurred roughly 2 billion years ago, when Abell 1367 plowed into Coma at a staggering 3,000 kilometers per second. The resulting shock would have rippled outward, growing fainter with time, yet the Coma relic remains anomalously bright, as if freshly energized by some unseen force. This persistent brilliance raises thorny questions. Normally, the electrons powering radio relics should lose energy rapidly, their radiation fading within 100 million years. The Coma relic's enduring glow suggests either continuous re-acceleration, perhaps by turbulence in the cluster's outskirts, or a reservoir of ancient electrons somehow preserved against all odds. Some theorists propose magnetic fields in the relic's region are unusually strong, trapping particles like flies in amber. Others speculate the shock wave might have encountered a dense filament of the cosmic web, reigniting its glow like a match struck against dry tinder. Then there's the relic's bizarre substructure. High-resolution images reveal intricate filaments and knotted regions within its diffuse glow, features that shouldn't survive in a simple shock wave. One explanation invokes multiple merger events, their shock fronts crossing and recrossing like tangled spider silk. Another possibility is that the relic is feeding on the cluster's own magnetic turmoil, its electrons whipped into frenzied spirals by chaotic field lines. Whatever the cause, these details make the Coma relic more than just a fossil. It's a dynamic, evolving entity, a laboratory for studying how energy dissipates across cosmic time. The implications ripple far beyond Coma. If relics can remain this vivid for billions of years, they might serve as permanent signposts of ancient collisions, helping us map the universe's large-scale structure. Their intricate textures could also reveal hidden properties of the intergalactic medium, from the strength of its magnetic fields to the density of its invisible filaments. And if their electrons are being re-accelerated by some unknown mechanism, it might hint at entirely new ways particles gain energy in the depths of space. For now, the Coma relic remains a puzzle written in radio static, its full story still waiting to be decoded. But one thing is certain. In the quiet outskirts of the cluster, the echoes of a forgotten cataclysm are still ringing loud and clear. Galaxies are supposed to follow a cosmic dress code, their colors determined by where they live. In the orderly universe we thought we knew, galaxies in dense clusters like Coma should overwhelmingly wear red and dead, their star-forming years long behind them, their once vibrant blue spiral arms faded into retirement. Yet when astronomers tallied the Coma Cluster's galactic population, they found a wardrobe malfunction on a colossal scale. A surprising fraction of galaxies stubbornly cling to hints of blue, flaunting star-forming regions that shouldn't exist in such a hostile environment. This isn't just a minor discrepancy, it's a full-blown rebellion against our models of galactic aging, forcing us to reconsider how environments shape cosmic evolution. The color of a galaxy acts like a cosmic birth certificate, encoding its star-forming history. Blue hues betray youthful vigor, signaling hot, massive stars burning bright and fast. Red tones tell of maturity, older stellar populations where only cooler, longer-lived stars remain. In most clusters, the transition from blue to red is swift and brutal. As galaxies fall into the cluster's gravitational grip, their gas, the raw material for new stars, gets stripped away by relentless ram pressure or siphoned off by tidal forces. Without fresh fuel, star formation sputters out, and the galaxy reddens like a fall leaf. Yet in Coma, this process seems delayed or disrupted, with too many galaxies caught in an awkward adolescence, neither fully blue nor completely red. One clue lies in their distribution. These discrepant galaxies aren't scattered randomly, they huddle along the cluster's fringes or trace filamentary structures feeding into it. This positioning suggests they might be recent arrivals, still clinging to reserves of gas as they make their first perilous plunge into the cluster's interior. But that doesn't fully explain their resilience. Some show signs of truncated star formation, not the abrupt quenching we'd expect, but a gradual decline, as if whatever's suppressing their star birth is working in slow motion. The plot thickens when we examine their gas content. Many of these galaxies harbor reservoirs of atomic hydrogen, the building blocks of new stars in amounts that defy cluster norms. Normally, this gas should have been torn away by now, yet somehow it persists. One theory points to magnetic fields wrapping around these galaxies like protective cocoons, shielding their gas from the cluster's onslaught. Another proposes that their orbital paths have been unusually gentle, allowing them to avoid the cluster's most violent regions. There's even evidence that some galaxies might be recycling their own expelled gas, capturing material blown out by earlier star formation and funneling it back into their cores like cosmic rainwater. Then there's the wild card of preprocessing. Before galaxies even reach Coma, they might pass through smaller groups where their gas is partially stripped or their star formation mildly suppressed. By the time they enter the cluster proper, they're already partially pre-quenched, leaving them in a transitional state that skews the color distribution. This would make Coma's galaxy population a palimpsest, a layered record of environments they've encountered over billions of years, not just the cluster's current conditions. The implications ripple far beyond aesthetics. If galaxies can resist reddening longer than expected, our timelines for cosmic evolution might need adjusting. Star formation, and by extension, the production of heavy elements essential for planets and life, could persist in clusters far longer than we'd modeled. It also raises questions about whether other clusters harbor similar anomalies, or if Coma's unique merger history has created conditions for this mismatch. Every blue-tinged galaxy is a clue, a whisper that the universe's rulebook for galactic aging might have more exceptions than we ever imagined. And in those exceptions lies a tantalizing truth. Even in the most extreme environments, galaxies find ways to cling to their youth. Nestled among the Coma Cluster's swirling galaxies lie ancient cosmic time capsules, globular clusters, dense balls of stars so old they've witnessed nearly the entire history of the universe. But when astronomers calculated their ages, they stumbled upon an impossible contradiction. Some of these clusters appear older than the cosmos itself. This isn't just a minor discrepancy, it's a full-blown cosmic crisis, forcing us to question everything from stellar physics to the very timeline of existence. Globular clusters are the universe's senior citizens, spherical collections of hundreds of thousands of stars, all born from the same primordial gas cloud. To estimate their ages, astronomers study their color magnitude diagrams, which plot stars' brightness against their hue. The key lies in the main sequence turn-off point, the exact moment when a star exhausts its core hydrogen and begins its retirement into red giant status. Since more massive stars burn out faster, this turn-off acts like a cosmic hourglass. The fainter and redder it appears, the older the cluster must be. In Coma, some clusters show turn-off points suggesting ages of 14 or even 15 billion years, a glaring problem when the universe itself is only 13.8 billion years old. How could something exist before time began? One possibility is that our measurements are flawed. Estimating cluster ages relies on models of stellar evolution, which assume certain initial chemical compositions and burning rates. If these clusters formed with unusually high helium content, something hard to detect from afar, their stars would burn faster, making them seem older than they are. Alternatively, if they're more metal-rich than we've assumed, their internal opacities could skew brightness measurements, tricking us into overestimating their age. It's like mistaking a well-preserved 50-year-old for an octogenarian because you didn't account for their skincare routine. But suppose the ages are correct. That opens the door to radical physics. Could these clusters have formed in a pre-Big Bang era, surviving some unimaginable transition into our universe? Most cosmologists dismiss this as fantasy, but other exotic solutions remain. Perhaps the early universe's expansion wasn't as smooth as we think. Local pockets of extreme density might have allowed stars to condense shockingly fast, like dew forming before dawn. Or maybe dark matter played a role, its gravitational influence accelerating star formation in ways our models don't yet capture. The wildest idea, time itself might not flow uniformly. Under general relativity, massively dense regions experience time dilation. Clocks tick slower near black holes, for instance. If these clusters formed in zones where space-time was profoundly warped, their local age could exceed the cosmic average. Imagine two candles lit simultaneously, one on a mountain, one in a valley. The valley candle burns slower due to stronger gravity. Observers at altitude would see it as older when compared. Could a similar effect apply here? The stakes couldn't be higher. If even a handful of Coma's globular clusters genuinely predate the universe, it would upend modern cosmology, forcing a rewrite of the cosmic dawn. For now, these ancient stellar congregations remain both a riddle and a gift. Their impossible ages a provocation, daring us to dig deeper into the laws that govern time, stars, and existence itself. And in their flickering light, we're reminded that the universe's history books may still have missing pages. The mysteries of the Coma Cluster haven't just puzzled astronomers, they've ignited a firestorm of debate, collaboration, and innovation across the scientific community. Picture a room where theorists scribble equations on whiteboards, observers scrutinize telescope data, and simulations spit out conflicting results, all because this single cluster refuses to play by the rules. The response hasn't been uniform. It's a vibrant tug of war between competing ideas, each vying to explain the unexplainable. Some researchers champion dark matter as the ultimate puppeteer, suggesting its elusive properties like self-interactions or hidden forces could account for the cluster's gravitational anomalies. Others argue for tweaks to Einstein's gravity itself, proposing theories like modified Newtonian dynamics, meant to explain why galaxies move faster than expected without invoking invisible matter. Then there are the wildcards, hypotheses involving primordial black holes, exotic particles, or even higher dimensions lurking in the cluster's shadow. This isn't just academic sparring, it's a race fueled by cutting-edge technology. The Chandra X-ray Observatory has been instrumental in mapping the cluster's searing gas cavities and violent jets, revealing energy budgets that defy expectations. Hubble's keen eye has captured ultra-diffuse galaxies in stunning detail, their ghostly forms challenging models of galactic evolution. Meanwhile, radio telescopes like ALMA and the Very Large Array eavesdrop on the whispers of cold gas filaments, while future missions like the James Webb Space Telescope and the Euclid spacecraft stand ready to probe deeper into the cluster's dark matter distribution and expansion rate tensions. These tools aren't just collecting data, they're forging new languages to interpret the cosmos. What unites these efforts is collaboration. The Coma Cluster has become a cosmic sandbox where cosmologists, astrophysicists, and particle physicists converge, sharing insights across disciplines. Large-scale projects like the Sloan Digital Sky Survey have turned the cluster into a living laboratory, with thousands of galaxies catalogued and analyzed by teams worldwide. Simulations, too, play a crucial role. Supercomputers crunching scenarios where dark matter clumps, galactic mergers, and black hole feedback are tweaked to match observations. Yet for every simulation that reproduces one anomaly, another inconsistency arises, keeping scientists on their toes. The stakes transcend Coma itself. If dark matter's behavior here proves unique, it could mean our universe hosts multiple flavors of the invisible substance, each dominant in different environments. If modified gravity gains traction, it would upend a century of astrophysical foundations. And if the cluster's missing baryons are found hiding in unexpected forms, it could rewrite the story of how matter cycles through the cosmos. The Coma Cluster isn't just a puzzle, it's a mirror reflecting the limits of our knowledge, and the scientific community's response proves one thing: when the universe throws a curveball, curiosity swings back harder. The Coma Cluster isn't just a cosmic curiosity, it's a laboratory where the universe tests the limits of our theories, forcing us to confront gaps in our understanding of everything from dark matter to the birth of galaxies. Take the cluster's missing baryons, for example. If half the ordinary matter in the universe has been hiding in plain sight, clustered in filaments or disguised as ultra-diffuse gas, it means our models of cosmic structure formation are missing a critical piece. We've long assumed that galaxy clusters evolved by steadily accumulating matter, but Coma's uneven gas distribution and rogue dark matter clumps suggest a far messier process, one where mergers and collisions scatter material in ways we're only beginning to map. This isn't just about filling in a cosmic ledger, it's about rewriting the story of how the universe organizes itself on the grandest scales. Then there's the dark matter dilemma. The cluster's gravitational lensing anomalies and lopsided galaxy motions imply that dark matter might not be the simple, passive scaffold we've assumed. Instead, it could interact with itself through unknown forces, clumping into invisible substructures or even flowing in hidden currents that slingshot galaxies to impossible speeds. If true, this would upend decades of astrophysics, pushing us toward exotic theories like self-interacting dark matter or warm dark matter, particles with just enough energy to move fast enough to smooth out small-scale structures. The implications ripple far beyond Coma. If dark matter's behavior varies by environment, it could explain why simulations of dwarf galaxies often fail to match real-world observations, or why some galaxy clusters seem to have too few satellites. Galaxy evolution models face their own reckoning. The survival of delicate spiral structures like NGC 4921, the premature quenching of star formation in some galaxies, and the bizarre resilience of ultra-diffuse systems all suggest that clusters don't just passively age, they're shaped by a complex interplay of tides, mergers, and feedback loops we've only scratched the surface of. Coma's overmassive black holes add another layer of chaos, hinting that the growth of these cosmic monsters might be less predictable than we thought, with some feasting far beyond their expected limits due to rare conditions in the early universe. If black holes can grow disproportionately large, they might play an outsized role in quenching star formation, ejecting gas, or even distorting the fabric of spacetime itself. And let's not forget the Hubble tension. The fact that Coma's local measurements of cosmic expansion clash with predictions based on the cosmic microwave background isn't just a technical discrepancy, it's a potential crack in the foundation of modern cosmology. If the universe's expansion rate isn't uniform, it could mean dark energy evolves over time, or that our corner of the cosmos sits in a rare void or overdensity. Some theorists even speculate about early dark energy, a fleeting force that altered the universe's expansion in its infancy, leaving behind fingerprints in clusters like Coma. Resolving these mysteries isn't just academic. The Coma Cluster's anomalies are a stress test for our understanding of physics itself. Every unexplained gravitational lens, every runaway galaxy, every ghostly radio relic is a clue that could lead us toward a deeper theory, one that might unite dark matter, dark energy, and gravity under a single framework. The stakes, nothing less than a new cosmic narrative, one where the universe's hidden rules finally step into the light. And if history is any guide, the answers won't just solve Coma's puzzles, they'll reveal surprises we haven't even thought to question yet. The future of unraveling the Coma Cluster's secrets lies not just in our curiosity, but in the revolutionary tools poised to turn science fiction into reality. At the forefront is the James Webb Space Telescope, already transforming our cosmic perspective with its infrared eyes. While Hubble showed us the cluster's violent beauty, Webb peers deeper, detecting the faintest stellar nurseries in ultra-diffuse galaxies, sniffing out molecular signatures in those enigmatic cold filaments, and even dating globular clusters with unprecedented precision to resolve their impossible ages. But Webb is just the opening act. The upcoming Nancy Grace Roman Space Telescope will conduct wide-field surveys of Coma's dark matter distribution, mapping its invisible scaffolding with a resolution that could finally reveal whether dark matter clumps truly lurk where lensing anomalies suggest. Meanwhile, Earth-based observatories are gearing up for their own breakthroughs. The Square Kilometre Array SCAR, a next-generation radio telescope network spanning continents, will capture the Coma relic in jaw-dropping detail, tracing its shockwaves down to scales of mere light years. This could settle the debate over whether the relic's enduring glow comes from continuous particle acceleration or some hidden energy source. Atacama Large Millimeter Array ALMA, already probing Coma's cold gas threads, will soon gain upgraded receivers capable of detecting faint carbon monoxide emissions, allowing us to track how these delicate structures evade evaporation in the cluster's furnace-like core. But perhaps the most tantalizing prospects lie in multi-messenger astronomy. The next generation of gravitational wave detectors, like the Laser Interferometer Space Antenna LISA, could sense the ripples from Coma's central black hole mergers, events that might explain the overmassive black holes we see today. Neutrino observatories like IceCube Gen 2 might catch particles flung from the cluster's particle beams, offering clues about their extreme acceleration mechanisms. Even dark matter experiments are joining the hunt. Detectors like LUX Zeppelin and Darwin could identify particles that, if they match Coma's gravitational anomalies, would rewrite particle physics. The horizon gleams with even wilder possibilities. Proposed missions like ESA's Athena X-ray Observatory will dissect the cluster's missing baryons by spotting the faint glow of warm, hot intergalactic gas. Advanced simulations powered by exascale computing will recreate Coma's entire history from its first galaxies to its modern chaos, with granularity that could predict where to find runaway galaxies or hidden dark substructures. And if the Hubble tension persists, dedicated missions like the Cosmic Dawn Intensity Mapper might uncover whether Coma sits in a cosmic void or if dark energy's behavior is more complex than we ever imagined. What makes this era extraordinary isn't just the technology, it's the potential for serendipity. Every time we've pointed a new instrument at Coma, we've stumbled upon the unexpected, ghostly galaxies, vanishing dark matter, particle beams defying physics. As these tools come online, one thing is certain: the cluster's greatest revelations may still be waiting in the shadows, ready to challenge what we think we know about the universe's grand design. The next decade of exploration won't just solve mysteries, it will undoubtedly create new ones, and that's the most thrilling prospect of all. From vanishing dark matter to ghostly galaxies, runaway stars to ancient cosmic relics, the Coma Cluster has proven itself a hall of mirrors for modern astronomy, each reflection revealing new layers of cosmic ambiguity. Let's revisit the enigmas that make this cluster the universe's most tantalizing puzzle box. We've seen regions where dark matter inexplicably disappears, defying the very scaffolding that should hold galaxies together. Ultra-diffuse galaxies, vast yet nearly invisible, float like celestial ghosts, their dark matter dominance challenging our models of galactic evolution. The colossal radio halo pulses with energy we can't fully explain, while the scorching hot gas at the cluster's heart somehow coexists with delicate filaments of icy material, cosmic contradictions that shouldn't survive side by side. Then there are the speed demons, galaxies racing at velocities that should eject them from the cluster entirely, yet something unseen holds them in place. Star formation quenches prematurely in some galaxies, while others cling stubbornly to youthful blue hues against all odds. Alignments of galaxies trace invisible currents, as if the universe sketched hidden blueprints we're only now glimpsing. Dark galaxies, devoid of stars yet heavy with mass, bend light like cosmic mirages. Overmassive black holes lurk in unassuming galaxies, their size defying every prediction. Gravitational lensing reveals mass where none should be, while vast cavities in the hot gas persist for billions of years untouched by time. The Coma relic etches a 2 million light-year scar across the cluster's outskirts, a fossilized shockwave from an ancient collision we can barely comprehend. Runaway galaxies flee the cluster's grasp like cosmic refugees, their trajectories hinting at violent pasts. The Hubble tension here magnifies a universal crisis. Our measurements of cosmic expansion refuse to agree, threatening the foundations of cosmology itself. And at the center of it all, an eerie quiet defies expectations, as if the cluster's heart has momentarily stilled, waiting. Each mystery is a thread in a tapestry we've only begun to unravel. The Coma Cluster doesn't just challenge individual theories, it confronts us with the humbling reality that the universe operates on rules we haven't yet deciphered. Perhaps that's the most profound lesson of all. For all our telescopes and supercomputers, the cosmos remains a story with chapters still unwritten, pages waiting to be turned. So what's next? Every anomaly here is an invitation to observe deeper, question boldly, and embrace the thrill of not knowing. Because the day we stop being surprised by the universe is the day we stop truly seeing it. If this journey through the Coma Cluster's riddles has sparked your curiosity, you're already part of the adventure. Hit like if you're as fascinated by these cosmic conundrums as we are. Subscribe to join us as we chase the next great discovery, and drop your wildest theories in the comments below. The universe isn't done surprising us, and neither are